Okay, number one, find the acceleration and tension in the rope between the two masses. So here's we need the tension right there, and these are the two masses. There's the force, must be 100 newtons. Here's my solution for this. So first I'm writing Newton's second law, F equals ma, and I guess I should really have the summation sign. So that's net force. The net force acting on this whole system is its mass times acceleration. And the net force is just this 100 newtons, because in this first part we're supposed to assume that the coefficient of friction is 0. So there is weight pulling these down and there's a normal force pushing them up, but those are equal and opposite. They cancel out. So the net force is just this. So plug in the net force of 100 newtons, plug in the mass of these two things because they're both being accelerated together, 20 kilograms, and A is what I'm looking for. So the acceleration is 100 divided by 20, which is 5 meters per second squared. And then we're looking for the tension in the rope between the two masses. So I want to know what this tension is. So now if I am just looking at the 5 kilogram block, before there's 100 newtons of tension in this part of the rope. 100 newtons is affecting both of these, but we just want to know the tension in this that's pulling this block along. So I guess I could draw another little picture over here. Here's the 5 kilogram block. Here's the tension pulling it to the right. That's the only force. So now the net force equals this tension. And that net force is also equal to mass times acceleration. We know what the acceleration is from the previous part, and we know what the mass is. So the tension is only 25 newtons. So if you're pulling this along, you're applying a 100 newton force to this rope, but this rope is only got a 25 newton force, which makes a lot of sense because you're pulling 20 kilograms and here you're only pulling 5. Number 2 is saying do the same thing but now have a coefficient of friction. This was frictionless, now there's friction. I've got this big diagram and I couldn't fill it all in right away, so some of these numbers I calculated and then put in as I went, but I'll just show you the diagram. So now we still got 100 newtons of force pulling the thing to the right, but I have 2 new forces that I needed to get in there. It was the force of friction, I'm calling it force of friction number 2, acting on the 15 kilogram mass, and force of friction 1 acting on the 5 kilogram mass. And in order to figure out what those are, technically I need the normal forces acting on both of these blocks. And so the 15 kilogram mass has a weight of 147 newtons pulling downward, and the surface is exerting that same force going up. So the normal force technically is the force of the surface, although it's really just going to be the same as the weight for a horizontal surface. So I got this normal force, and I've also calculated a normal force here, which is the same as the weight of this block, which is mass 5 kilograms times g, which is 9.8. It's 49. So that's how I came up with the 147. 15 kilograms times 9.8 is 147. So I got the 2 normal forces, and now I need the forces of friction. And here's the formula for force of friction. Force of friction is equal to mu times the normal force. So for the 5 kilogram block with the normal force of 49, it's 0.2, which is mu in this question, times the normal force. So you get 9.8 newtons. And then the force of friction acting on this block is coefficient of friction times the normal force, 29.4 newtons. Now, I've got arrows showing this is pointing to the left, and I'm calling them positive here. You could call them negative, but we'll get to that in a second. So I've got all the forces that are acting here. I've got force that's pulling this rope, and then I've got the force of friction from this block pulling to the left, the force of friction from that block pulling to the left. So my net force is what I get if I add all those up. So here's where the signs come in. 100 newtons, that's my pulling force, minus the force of friction on this block, minus the force of friction on this block, minus the force of friction on that block. So this minus this gives me the net force. So that's net force written as the sum of all the individual forces. I could add these forces up, but this is going to be positive 147 and that's negative 147, and you get 0. So these cancel out, so I don't include them. So it looks like I substituted in the actual values here. 100 newtons minus 98 newtons, sorry, that should be 9.8 newtons, minus 29.4 newtons is 60.8 newtons for the net force. Another way to write the net force is mass times acceleration. So again, the reference frame here is the entire system. So this was the net force for the entire system. And when I write F equals ma, I want to do that for the entire system. So the mass that I use is the sum of these two masses, 20 kilograms. And A is what I'm looking for. So force equals ma. And I set that equal to 60.8. So this is using Newton's second law. This is just adding up all the forces, setting them equal to one another here, which allows me to solve for A. So the acceleration is 60.8 divided by 20, 3.04 meters per second squared. Now the other part is to find the tension in the rope between the two masses. So this is the tension right here. So I could actually show tension pulling this block to the right, and tension is pulling that block to the left. It's the same force. They're equal and opposite. They cancel one another out if I write them like that. This is to the right, this is to the left, which means as this thing is being pulled, these blocks are not moving to the left relative to one another or to the right. They're staying the same distance apart. But I'm not going to look at this one. I'm just going to look at this tension and this block. So I've redrawn this picture down here. I might as well write 5 kilograms. So this block just has two forces acting on it that are important. It's got the tension pulling it to the right, it's got the friction pulling it to the left. It's also got the normal force and weight, but those cancel out. So I'll write the net force two different ways. Here's this first one, you can't see it, I hole punched through it. Net force as the sum of the forces, which would be the tension, which is positive, minus the friction, which is going the other way. I'm saying this is positive and that's negative. So tension minus friction is the sum of the forces acting on it. And since I know the force of friction, I already figured that out up here, 9.8. It's T minus 9.8. Then I'm using Newton's second law, F equals ma. The mass of this block is 5. The acceleration, I already figured out over here, 3.04. So F equals ma gives me this for the net force. Adding up all the forces gives me this for the net force. So these two things have to be equal. They're both the net force. And when I multiply that out, I get 15.2 newtons equals T minus 9.8. So I add 9.8 to both sides and I get 25 newtons equals T.